Hello, welcome back. The title of this lesson is called The Laws of Logarithms. So in this lesson, what we're going to do is really dive into the properties of logarithms and some of the most important core laws of logarithms that you're going to be using over and over and over again. So this material is every bit as important as things that you might have learned in the past, like laws of exponents or laws of radicals. The laws of logarithms are things that you would use through the rest of algebra, in pre-calculus, in trig, in calculus, in 1, 2, and 3, and on and on and on, because logarithms are not going to go away. So what I want to do in the beginning is I want to just have them on the board. I don't want to hit you over the head with them, but I want to talk to you about what they really mean. And then we're going to solve some problems in the next few lessons to use these laws of logarithms so you know how to use them. And I have a lesson, about 2 or 3 lessons from now, where I'm going to derive all of these. So if you want to know where these laws come from, I want you to kind of stick with me, and we'll do that a little bit later. I don't want to bog the discussion down in the beginning with deriving where they come from until we get some practice. But if you stick with me, we will talk about exactly where these laws come from. And it's very, very understandable. So here are the laws of logarithms. I have 5 of them on the board here. Typically, in most books, you're only going to see 3 laws. You'll probably see these 3, 4, and 5. You'll see them boxed in on your paper. Number 1 and number 2 on my board, I think, are so important, so that's why I want to have them up at the top, because really and truly, when we learn logarithms, we learn them for a reason. We use all of these laws, but we use number 1 and number 2 all the time in dealing with equations and in calculus and trig and other places down the road. So they're so important, I want to put them here. So even if your book says there's only 3 laws of logarithms, I want you to now know there's really 5, at least what I consider to be 5 laws of logarithms. The first 2 come from the fact that a logarithm is an inverse function from the exponential function. If you don't remember that, then you need to go back to learn my basic lessons in what a logarithm really is. But if you remember, what we have inverse functions, is we have a function number 1 and function number 2. In this case, an exponential function and the logarithm, which they're inverses of one another. If we stick an input into the first function, calculate a result, stick that thing into the second function, the inverse function, what it does is it kind of undoes, or it reverses the calculation of the first function. That's what an inverse does. So when you put a function with its inverse and put them in a chain like that, basically it kind of undoes the first function, and what you get back is exactly what you started with. That's what an inverse function is. And that's what these first 2 laws are telling you. What we're saying is the base b logarithm, you have to replace b with a number. You know, all these logarithms have numbers. Base 2 logarithm, base 10 logarithm, whatever. So in this case, we're keeping it general. We're saying the base is b. If you take a base b logarithm of something that is itself an exponential b raised to the power of some number k, then what happens is the logarithm kind of undoes, or it annihilates, the exponential. They kind of cancel each other, and all you get back is k. That's extremely important for you to remember, and in my opinion, most books don't emphasize it enough. It is one of the most important, most useful, most critical things for you to understand about logarithms. They can undo or annihilate, or if you want to use a rough word, they can kill an exponential. So here you have this exponential, b to the power of k. It could be 2 to the power of 3, or 3 to the power of 5, or whatever. If I take a logarithm that has the same base of that whole thing, then the logarithm kills the exponential. They disappear, and all you have left is k. So you can see right away how it's useful for solving equations, because a lot of times I want to solve for something, but I may need to kill that exponential to get rid of it. So that's how I'll do it with a logarithm. Now, the law number 2 is exactly the same thing in reverse. Just like a log can kill an exponential can kill a logarithm. See here, we have a logarithm, a base b logarithm of some number, but we take that whole thing and we raise it b to the power of that. So we have an exponential base b, but what we're taking the exponential of is a logarithm, again, same base b. So the exponential cancels or annihilates the logarithm, giving you the number back. Now, if you remember back to inverses and discussions of inverses, we did a lot of that recently. Again, you take an input into the first function, then run that through the inverse, and what you get back is exactly what you put in. That's what an inverse function is. So here, if you think about it, if the input to this whole process is k, right, then the first function you run it through is b to the power of k. And then you take that result and you run it through its inverse, which is a logarithm base b. So you take an input of k, run it through the function, which is an exponential, then do its inverse, which is the logarithm. So they all kill each other, and all you get back out is what you start with, k. Here, you're taking the logarithm of a number n, right? And so you're running it through the first function, which is a logarithm, And then you get the result of that and you do its inverse. You take b to raise to that power, which is the inverse of the logarithm. So they kill each other again and you get what you start with. See, both cases you get what you started with. That's what an inverse function is. Okay. Now the rest of these guys, we're going to use them as we kind of encounter problems here in just a minute. And I'm going to derive all of these in a future lesson, as I said. But basically, when you have two things multiplied together and you take their logarithm, then it becomes like addition of logarithms. So multiplication of things, functions or numbers, when you take the logarithm, becomes addition of logarithms. So multiplication becomes addition of logarithms, okay? Likewise, division of numbers, once you take the logarithm, becomes like subtraction. So it's kind of like, it's like a transformation rule. Like multiplication kind of becomes addition of logarithms. And division kind of becomes like subtraction. Not kind of, it is subtraction of logarithms. It's kind of a transformation. If you don't like working with multiplication, no problem. You can make it into addition. You got to take logarithms first, though, to make it happen. But you can do that, right? If you don't like division, maybe it's really hard to do, take the logarithm. Then your division goes away, and you only have subtraction. So some problems are really hard. Maybe you have a very complicated division of two very complicated things. No problem. Take the logarithm and then the division goes away. It becomes subtraction. But then you have the added baggage of you have to take logarithms, right? And then our last one here is the odd man out, I guess. These kind of go together and these kind of go together. This is kind of the odd man out. And so basically, if you're taking the logarithm of something raised to a power, something raised to a power. Notice the base is not the same like it was up here. Like it could be different, right? So anyway, what you can do is take this exponent and bring it to the outside of the logarithm. So basically everything else stays the same. Logarithm base b of m, that's here. We just take the exponent and we go backwards and we can pull it out in front. K times the log of that. So that's very useful as well when solving some equations. So again, multiplication of things becomes addition when you're dealing with logarithms. Division of things, again, becomes subtraction when you're dealing with logarithms. Exponents becomes where I can just take the exponent out and bring it onto the front times the logarithm of the basic expression. And then the other two at the top just basically mean that exponentials can annihilate logarithms and logarithms can annihilate exponentials. Okay, in words, that is going to save you so much time because in most textbooks you flip the page and you don't even know what they're trying to say. This is all you need to know. Now what we need to do is start solving some problems, simplifying and solving some simple simplifications using these laws of logarithms. So what we're going to do is get started with that right now. Let's take our first problem. What if I give you, I want you to simplify the following. Logarithm base 2 of the number 2 to the 4th power. What is that equal to? Now in the past, the way you would do it would be a different way. We'll talk about it in just a second. But now that you know that logarithms can annihilate exponentials, just giving you back what's in the exponential, then you look back here and you say, that's exactly what I'm doing. I have an exponential 2 to the power of something. The base is 2. But I'm taking the logarithm of that thing with exactly the same base. So the logarithm completely annihilates the exponential, and all you have is a number 4 that comes out. The 4 goes through the function, then it gets run through its inverse with the same base, and so what you get back is what you started with, which is the number 4. Now the old way that we would do that, so you can just write this down without any math. If you know that they annihilate, you can just write it down. But the way we would do it in the past is we would say the base to the power of something has got to equal to what we're taking the logarithm of, which is 2 to the 4th power. And you can then see, since the bases are the same, x has to be equal to 4. And so this logarithm reduces to 4. So you see, these laws of logarithms really are not that different from what you've been doing before, but a lot of times, especially with very large equations, it's going to be much easier to understand these rules and use them rather than some of these other techniques that we have learned. All right, let's take a look at the next problem. Let's say we have logarithm base 5 of the number 5 to the power of 6. Again, you don't have to calculate anything. You have a base 5 to the power of 6. This is an exponential, but you're taking a logarithm of that thing. So the log of the exponential, same base, means they annihilate each other, and all I have left is a number 6 back. Because I take that 6, I run it through this exponential function, then I take the result and I run it through its inverse, the logarithm, and so everything annihilates and I get what I start with. Again, it would be the same thing as the way we have done it before. You would say base 5 to the power of something is equal to what I'm taking the log of, 5 to the power of 6, and you then know that x is equal to 6. So you could do it that way if you want. I'm just trying to show you how to use the laws of logarithms here. All right. Now let's switch gears a little bit. Instead of taking the log of an exponential, let's take the exponential of a logarithm. Let's say we have 2 to the power of logarithm base 2 of the number 7. So this is all in the exponent of the 2. So it's exactly reversed. Instead of doing the exponential first and then taking the logarithm, here we're going to take the logarithm first, and then we're going to take the answer and raise that to the power of 2. So notice how you have a base 2 and a base 2 here. So this exponential completely cancels with the logarithm, and you don't even have to do any math. You just say the answer is 7, right? You just say that the answer is 7. And that comes back to this rule right here. It's a little harder to read without numbers, in my opinion, but that's what it's saying. Base b raised to a logarithm with a base b of some number. The logarithms completely annihilate the exponentials, and so you're just left with what you start with. Because you've taken this 7, you ran it through a logarithm, base 2, you got the answer, then you ran it through its inverse, which is an exponential with the same base, and so you get back what you start with. That's what an exponential is. Or that's what an inverse function is. All right, what if we have 11 raised to the power of the logarithm base 11 of the number 3? Well, you can see right away, you have a logarithm base 11, you're taking that thing and you're saying the base 11 raised to that, so the exponential annihilates with the logarithm, and you could say that the answer is 3 without any further work, because it falls directly under the laws of logarithms. I'm doing these kind of simple problems with numbers because I want you to understand what the laws are really saying, but you're going to have to trust me here. When you get to more advanced math, you might have an entire equation, which is an exponential, and you want to kill that thing, so you're going to take a logarithm of both sides in order to kill whatever it is you're trying to isolate or to simplify something. And so knowing these laws will save you a ton of time when doing real problems. All right, let's do something a little more challenging. Let's say we have 8 to the power of 2 plus x. Now this 2 plus x is all in the exponent of 8, of the number 8, is equal to 2. And I want to solve this equation. Now actually, this equation, we've solved it before. Because remember, we learned about the exponential function, and then we learned how to solve exponential equations. And the way we solved it before is we said, okay, I can write 8 as 2 to the power of 3. So I can say this is 2 to the power of 3, and that's raised to this. And then when I do the multiplication and set the exponents equal, I can solve for x. We've done that in the past. I'm going to show you an alternative way now that you understand the laws of logarithms. Notice that when I take a logarithm of an exponential with the same base, it kills it, and I just get back what I start with here. So that's what I have. I have an exponential with a base raised to the power of k. A base raised to the power of quote-unquote k. So if I want to get rid of this exponential, right, I can take the logarithm of both sides. So I'll take the logarithm, and I'm going to take the base 8 logarithm of the quantity 8 to the power of 2 plus x. I'm taking the logarithm of the whole thing. And if I do it to the left, I have to do it to the right because that's how equations work. So you see, I'm allowed to do what I want to both sides. I'm going to take the base 8 logarithm. Why am I choosing base 8? Because this exponential has a base of 8. So I know from the laws of logarithms, if I take a log base 8 of an exponential that also has a base 8, then the exponential completely annihilates with the logarithm, and all I have left is what I started with in the exponent 2 plus x. It's gone. It's like, I don't want to strike through it, but it's like you could just strike through it. It's gone. They cancel each other. It's like adding 2 and then subtracting 2. You don't have any change. It's like multiplying by 5 and then immediately dividing by 5. Running something through an exponential and then immediately through a logarithm of the same base just undoes the whole thing, and you get back what you started with. In this case is what the exponential is where you started. It goes through the exponential and through the log. That's what you get at the end. On the right-hand side, you still have to deal with this log base 8 of the number 2. That's true. That's there. But we know how to do logs, so let's go ahead and solve this. Let's go off here to solve that. Log base 8 of the number 2. How do we solve that? It's the base 8 to the power of something is equal to 2. But you know that 8 can be written as 2 to the power of 3. That's all I did there. So you multiply the exponents. 3 times x is 3x. And I can equate these exponents. 3x is 1. So then x is 1/3. I did all this on the side just to figure out that the right-hand side was equal to 1/3. So I have 2 plus x is 1/3. So all I have to do to solve this equation is say that x is 1/3 minus 2. Right? Now, a lot of you can do this kind of thing in your mind, in your head, that's no problem. But for those of us who can't, this is what you would do. You have to get a common denominator. So you have 1/3 minus 2 over 1. That's what you're subtracting. But then I'm going to multiply this fraction by 3 over 3 so I can get a common denominator of 3. So I'm going to have 1/3 minus 2 times 3 is 6, 6/3. And so what I'm going to have is x is going to be equal to, the common denominator is there, so 1 minus 6 is negative 5/3. What were you trying to do? You were trying to solve for x. And that's what we did. We solved for x. Now it's a little confusing because when I came over here, I also introduced an x. This over here was just for the purpose of finding out what this logarithm was. I should have used probably a different variable here. I could have used y or a or b or anything else just to use a dummy variable to calculate this. But you see what we're doing here? You might argue with me and say, well, taking the logarithm of both sides is way harder than the other way we did it. The other way we did it, we just wrote 8 as 2 to the power of 3 raised to this power, and we go through it. We've done that before. It's actually easier to solve it using the other techniques, but that's not the point. The point is, I'm trying to teach you how to do logarithms, how to use logarithms, because I promise you, there are many, many problems where it's much, much faster to use a logarithm. So we have to kind of crawl before we can walk. A little more work here, but we get the same answer here. If you go back to your notes, we already did this problem before, you get exactly the same thing. So the first couple of problems were mostly geared in trying to get you to understand how to solve these equations. The next few problems are going to be, well, it's a mixture, but we're going to be trying to use a little bit more of the last 3 laws of logarithms. Remember, multiplication, when you're dealing with logarithms, becomes addition. Division, when you're dealing with logarithms, becomes subtraction. And raising to an exponent just pulls the exponent out in front, and it's a log of whatever it is you were doing to begin with. So let's slide over and try to tackle a few more to give us some more practice with that. What if I have logarithm base 9 of the number x is negative 1/2? Now, there's, I guess I lied to you a little bit. We're probably going to be using a little bit more of the first couple of laws here. I forgot about this problem. But how would you solve this? You want to figure out what this is. There's lots of ways to do it. We've solved this problem before. You already know you can solve this by saying 9 to the power of this is equal to this. We've solved that exact problem. 9 to the power of that is equal to x, and boom, you solve for x. That's not the point here. The point is for me to teach you how to use these laws of logarithms to solve problems we've already done. So how would we kind of get rid of the logarithm? We would have to do the exponential to both sides. We have to use the exponential, but it has to be the same base. So I can write this as 9 to the power of log base 9 of x. And then if I do that on the left, I have to make it 9 to the power of 1/2 on the right. I make this an exponential with a base 9, this exponential with a base 9. I know I have the same bases. Exponential cancels with the log, so I'm left with x. 9 to the negative 1/2. Notice this is exactly what you get if you say 9 to the power of this is equal to this. 9 to the power of this is equal to this. Using the laws of logarithms and using the techniques we've learned before yield exactly the same thing, so you know you're on the right track. So what we have here is 1 over 9 to the 1/2, and so you get x is 1/3 because the square root of 9 is 3 there. Same answer as before. This problem and the last one, we've already solved those problems. All right, so now we want to switch our gears to using law number 3, law number 4, law number 5. So what we want to do here is write in terms of log base 2 of m and log base 2 of n. You'll see what I mean when I give you the first problem. That's how we're simplifying these. So what if I give you log base 2 of the quantity m to the 6th power times n to the 3rd power? Now you have a little bit of a combination of things happening here. You have two things multiplied together, but you also have exponents in there. So remember, when you have two things multiplied together and you're taking the logarithm, you can just break them apart and make it the logarithm of both of those things. So do that part first, right? So what's this going to be? Logarithm base 2 of m to the 6th plus logarithm base 2 of n to the 3rd, because these are multiplied together just like it was in the law. So this thing is a logarithm of that, this thing is a logarithm of that, and we add them together. So the multiplication's now gone, it becomes addition. But then we remember our last law of logarithms is that anytime we're taking the log of something with an exponent, we can take the exponent out in front and just take the log of what is left over. And again, we're going to prove all of these later. We haven't done that yet, but we have exactly that situation here. The 6 can come in front of the log, making 6 times log base 2 of m, plus sign stays here. The 3 can come out in front, log base 2 of n. 6 log 2 of base 2 of m, 3 log base 2 of n. This is the final answer. So we had to write these in terms of log base 2 log of m and base 2 log of n. That's exactly what we've done. All right, put a little dot here if you want to denote the multiplication. All right, how many more problems do I have? I think I have enough. I think I want to do one more problem on this board. And yeah, I think I want to do one more on this board. And then I have plenty of space on the other. What if I have log base 2 of the number m times the square root of n? So I have two things multiplied together, of course. And so when I have two things multiplied together, what do? I break this guy up into its own logarithm of each thing and I add them together. Multiplication becomes addition when you're dealing with logarithms. So what do I have here? This is going to then become log base 2 of m plus log base 2 of, what is this? Square root of n. It's just another number. Square root of n. Now, if you circled this on your paper, I probably would give you most credit because at this point you know how to apply the law of logarithms. You've recognized you're multiplying something, so you break it apart and make it addition of logarithms. That's fine. But there's a little bit more that you can do here because if you think about it, what this is really equal to is log base 2 of m plus log base 2. This radical can be written as n to the 1/2 power. So this exponent here on this second term, we can use this one here to pull the exponent in front. And that's going to basically make it a little bit simpler. Because notice, we want to write it in terms of this and this, but this is square n to the 1/2. This is not log of n, this is n to the 1/2. So we have to do something to get it there. Log base 2 of m plus the exponent comes out 1/2 times log base 2 of n. This is the final answer. Log base 2 of m plus 1/2 log base 2 of n. Now we have written it in terms of this and this. The previous step, even though it kind of was halfway there, really wasn't because this is the log base 2 of the square root of n. That's not exactly what we were trying to accomplish. All right, we have two more just to get kind of our feet wet and continue working on this. And what if we have log base 2? Again, I'm using base 2 a lot, you know, base 2 here for this problem, but just keep in mind these laws of logarithms apply and are used for any base of m to the 4th power over n to the 3rd power. So it's a base 2 logarithm of the quotient. And if you remember, anytime you're dividing in something inside of a logarithm, it becomes subtraction of the logarithms. So that's what you have to really do there. And so then what we're going to have then is log base 2 of m to the 4th power minus log base 2 n to the 3rd power. So you've effectively split this up in the subtraction, but then you realize you have these exponents here. So we'll use the other law of logarithms, pull the exponent in front, 4 times log base 2 of m minus the 3 can come down, 3 times log base 2 of n. And this will be the final answer. 4 times base 2 log of m minus 3 times log base 2 of n. That's the correct answer. All right, we have one more. This one's a little bit longer, but it's not that difficult. You just have to take it one step at a time. What if you have log base 2 of m over n cubed, but this whole thing has a square root around it? That's what you're taking the logarithm of. So it looks like a lot of stuff to unpack, and it is. So let's go all over here and do it one step at a time. This whole thing has a square root around the whole thing. So first we need to get rid of that and make it a fraction. Log base 2 of m over n to the 3rd power. But this square root now becomes a power of 1/2. You always want to do that pretty much all the time. Make your radicals into exponents like this. All right? Now you're taking the logarithm of something, this whole something here, raised to the 1/2. A lot of students will look at this and start trying to apply this rule to subtract the logarithms, but you got to look bigger picture than that. The thing that you're doing on the outside of that is this whole thing is to the 1/2 power. So the proper thing, order of operations wise, is to take the 1/2 out in front times log base 2 of m over n to the 3rd power, like this. So you're taking that exponent out. Now you're taking the base 2 log of a straight quotient like this. So then what you'll have is, now this 1/2 is multiplied times the log of the final result. So you have to really should open up a bracket or parentheses, because this is going to expand to logarithm base 2 of m minus, because it's division, logarithm base 2 of n to the third power, because that is what is on the bottom. Now this whole thing is in a bracket because it's 1/2 times this. This happens to be this. So there's a bunch of different ways you can do it if you want. Let's just do it like this. Let's keep the 1/2 on the outside. Log base 2 of m minus. Now this is a log, but you have a power here. So this power can drop down also. 3 times the log base 2 of n. And then you have 1/2 times this whole thing. So then, when you multiply the 1/2 in, you have 1/2 times log base 2 of m minus. When you take the 1/2 times the 3, you're going to get 3/2 log base 2 of n. Let me double check myself. 1/2 log base 2 of m minus 3/2 log base 2 of n. This is the final answer. This is the most simplified form. Remember, we're trying to write them in terms of log base 2 of m and log base 2 of n. So these problems are specifically crafted to get you, to force you to use the laws of logarithms. And you can see that rarely are you doing just one or the other. Like in this problem, we had to deal with the exponent, bringing it down. Then we had to do the subtraction because it was a quotient. Then we had another exponent to bring down. Then we had to multiply the 1/2 back in. So we were doing a lot of different things. And so you can see these laws of logarithms, they work together. So again, to recap, there are 5 primary laws of logarithms that I want you to really remember and burn in your mind. When you have the log, base b, of an exponential with the same base, they kill each other and you just get back the exponent. When you have an exponential of a logarithm, same base, they kill each other and you just get back what you were doing the logarithm of and the exponent there. When you multiply things and you take the logarithm, it becomes addition of logarithms. When you divide things and take the logarithm, it becomes subtraction of logarithms. And when you have an exponent of something raised to something else powered, the exponent can always come out in front of the logarithm multiplied by a logarithm of what's left over. Same base, obviously. Where do these laws come from? We've talked about extensively where the first 2 come from. The last 3, I haven't given you any proof of where they come from. But I promise you, they're not hard to understand. What I want to do is make sure you understand all of these problems. Solve them yourself. Make sure you grab a paper and solve them yourself. Go and do the next lesson or 2 with me. Get some more practice with using these laws, and then I have a lesson on the books that I'm going to show you and derive exactly where they come from so you'll understand where everything is. So solve these yourself, follow me on to the next lesson, and continue to conquer and practice the concept of the laws of logarithms.